Hop. Voilà. Okay, so we have this notion of strong equivalence. The problem is that it's difficult to determine when two objects are strongly equivalent. So we use this weaker notion of equivalence, which is either quasi-isomorphism or weak homotopy equivalences or weak homotopy equivalences of topological spaces. And this is simpler to determine in general, but the thing is that it's only equivalent to strong equivalences for some objects. So either projective complexes in chain complexes and CW complexes in topological spaces, when you are most interested in when you can map from the objects, or if you want to map into the objects, in chain complexes, it's injective complexes, and in simplicial sets, it's scan complexes. And these are characterized by lifting properties with respect to some class of maps. So either surjections, in the case of chain complexes for projective objects, or Serre and Hurewicz fibrations for CW complexes, or Can fibrations. And the dual part is injective objects, which are defined as something which have lifting property with respect to injections, cofibrations, or inclusions of subcomplexes. So what we are going to try to define is a framework which encompasses these common features between these three categories in which we can do homotopy theory. Okay. So any questions before we start? No? Okay. So let me remind you of the definition of a model category. So a model category is the data, first of all, of a category, a class of cofibrations, a class of fibrations, and a class of weak equivalences. Okay, so weak equivalences are the most important part. Typically, I denote them like that, an arrow with a small wave on top. Okay, so you should think about them as quasi-isomorphisms or weak homotopy equivalences. Okay, so this is what we are interested in. We want to classify spaces up to this notion of equivalence. Then you have C, which is the data of cofibrations. So typically, I will denote them like that with a small hook at the top of the arrow. In some books, you can also find this notation like that. So just be aware of that. And usually, there is a class of fibrations. So typically, I will denote them like that, but you can also find this notation in some books. Okay, and so you should think about them either as, so for fibrations, it would be surjections or Serre or Hurewicz fibrations or Can fibrations. And usually cofibrations, you should think about them as injections or cofibrations or inclusion of subsets. Okay, and these are extra data which will allow us to make concrete computations in our category up to homotopy. Okay, this is something extra. This is what we really want is this part, weak equivalences part. And this is extra data which allow us to do concrete computations in our category. Okay. And we have to add these two extra data, cofibrations and fibrations. You should not be confused because in topological spaces, we only have one piece of the data, the cofibration part, which is relevant because everything is good when you map into it. Whereas in simplicial sets, it's the reverse. Everything is good when you map into it. That is good when you map out of it, sorry, but not all of them are good when you map into them. And so to encompass both cases, we need both. And there are also some model categories in which we really need both. Some objects are good, are are not good either when you map out of them or into them. Okay. So MC1, the axiom is that M is complete and co-complete. So it admits all small limits and co-limits. Okay. So this one is pretty standard, and all examples we are going to see are going to be satisfied without problem. Then W satisfies the 2 out of 3 property. Okay. So I will either call this property 2 out of 3, or I will call it MC2. Okay. The axiom numbers are arbitrary, of course. We can reorder them if we want, but this is the classical order. Also, they are pretty much in order of increasing difficulty when you want to prove them. This one, M is complete and co-complete. Typically, this is something about your base category that is either true or not. This one takes a bit more work to prove. MC3 is also a bit more work. And the real difficult part is MC4 and MC5. Okay. You are going to see it in examples. So if you have a commutative diagram like this, so G circle F, F and G. So if 2 out of are weak equivalences, then so is the third. Okay. So as I said Wednesday, this is really 3 axioms in one. If F and G are weak equivalences, then so is G circle F. If F and G and if F and G circle F are weak equivalences, then so is G. And similarly, if G circle F and G are weak equivalences, then so is F. So typically, this axiom is not really hard to check. Why? So you can see it in all these examples. Very often, weak equivalences are defined as something which are sent to isomorphisms in some category. Okay, so here you have a functor homology, and something is a quasi-isomorphism if it is an isomorphism when you apply this functor. Okay, and something defined like that always satisfies 2 out of 3. I will say it right now. Okay. So if you have some functor like that, and you define W as F minus 1 of isomorphism, then this satisfies 2 out of 3. Because I will do one of the 3 cases, the other 2 are pretty much also obvious. So proof, if F, G are in W, then F of G are iso. And if you compose 2 isomorphisms, it's still an isomorphism. But of course, because this is a functor, this is F of G circle F. And therefore, G circle F is in W. And you have something similar for the other cases. If you have, what I'm saying is that, first of all, isomorphisms always satisfy 2 out of 3. And second, if you take the preimage of isomorphisms under a functor of something which satisfies 2 out of 3, then the preimage satisfies 2 out of 3. So this is something that we are going to see quite often. In model categories, weak equivalences are very often defined as preimages of isomorphisms under some functor. And so this axiom pretty much comes from 3, right? Okay. So axiom MC3. says that if F is a retract of G and G is in W, or G is in C, or G is in F. Oh, sorry. Then F is in W, or F is in C, or F is in F. It as I did. Okay, so again, this is 3 axioms in one. It says that if you have a cofibration and you have a retract of that cofibration, then you still keep a cofibration. Similarly for F and for W. So one first remark is that isomorphisms satisfy that, right? If you have a retract of an isomorphism, it's not hard to prove that it's actually an isomorphism again. Easy exercise that you can try to do at home. And then you are going to see in examples, very often C and F will be defined as something which has some kind of lifting property, and something which is defined as a lifting property always satisfies this axiom, MC3. But we are going to see it in examples. Okay. Okay, so this one is already a bit harder because this is something about the 3 classes of morphisms and not just one, but very often it will come from 3 or almost. Okay. Now we get to the really more difficult part. So consider a square like that. Where I is a cofibration and P is a fibration. Okay, so you have a square. On the left, you have a cofibration. On the right, you have a fibration. Then you have 2 parts of this axiom. Part 1 is if I, okay, maybe I will try to order them as I did in my notes. So if P is a weak equivalence, then there exists a lift L. So a morphism which makes both triangles commute. So if this is F, this is G, this means that L circle I is F and P circle L is G. Okay. And axiom 2 is very similar. If I is in W, then there exists a lift L. So same results, except that the hypothesis is different. So the way to think about it is you have a square. This one is a cofibration. This one is a fibration. And one of them is a weak equivalences. Not necessarily the both of them, but at least one. Okay. And final axiom, MC5, and this is typically the hardest axiom to check. Because so far, as I mentioned Wednesday, if I take the empty classes for these 3, then okay, MC1 is something that is either true or not. If W is empty, then this is satisfied. If C and F and W are empty, this is satisfied. If they are empty, this is satisfied. But this one tells us that we are not talking about the empty set. So for every morphism A to X, there exists 2 factorial factorization. So either you can start with a cofibration and followed by a fibration, which is also a weak equivalence. Or you can start by a cofibration, which is a weak equivalence, followed by a fibration. Okay. Okay. So I gave some names to the intermediate objects. They should make you think about either the cylinder here, and here about the path space. Because let me write what I mean. So in top, if you have a map, sorry, maybe let me call them A and X as in my axiom. How to factorize F as a cofibration followed by a weak equivalence, which is a fibration. You can take what is called the cylinder of the map F, which is A cross 0, 1 union A cross 1 with X. Okay. This is a cofibration. And then you can project down to X. So this part X, you just take the identity. And if you have an element of A cross 0, 1, you just send it to F of A. Okay. And this is a fibration, and this is a weak equivalence, because you can just contract the interval and you only have X left. Maybe if I draw a picture, this is X, this is A. You have glued a cylinder onto X, okay, along F. So if you contract this cylinder, this is a weak equivalence. Okay. So this should make you think about this axiom. And the other one is something like that. Cross A. Okay, let me answer your question once I'm done writing that. So here, this is kind of a dual construction where you take the path space, you take the space of all paths inside A, and you wait, this is not right. It's not right. You take here X. Well, okay, I want to write this part. I know what's wrong. Okay, this is the space of all things in X. So this is all pairs like that, A in A, such that gamma of 0 is F of A. Okay, so this space, which you can write as a pullback, as I did here. So this inclusion is a weak equivalence. The inclusion just sends a point A to the constant path equal to F of A. Okay, and you can contract the interval. So this is harder to visualize because we are looking at a function space, so it's infinite dimensional. But you can contract the interval back to the starting point, and the starting point was F of A. And so in the end, all that remains is the information of A. And then you can project to X by evaluating your path not at 0, but at 1. And this is a fibration. Okay. Is this clear before I answer the question in the chat? So this is more for the intuition of the Axiom Mc5 than anything else. Huh? Okay. So there was a question about the functoriality. So for the functoriality, you have to look at the arrow category of M. The objects are morphisms like that. and the morphisms are commutative squares like that. I hope it's clear what I mean. Yeah. If you have two morphisms in your base category, it's an object of the arrow category. And a morphism in this arrow category between these arrows is a commutative square like that. So a pair of morphism between the sources and the targets, which make the things commute. Okay. And so it means that if you have such a commutative square, then you have something like that. For example, if I take the cylinder, if you have something which makes the outer square commute, then you have a map between the cylinders, which makes both squares commute. Okay. So this axiom is a bit tricky, so that's a good question. In the first definitions that were given of model categories by Quillen, it was only assumed that there was a factorization. No assumption about functoriality was made. It turns out that, first of all, this is very convenient to have factorial factorizations. I will use them again and again. It doesn't mean that it's impossible to do the theory without it, but it's easier. Second, most examples have actual functorial factorization. So people said, what the hell, let's just add this axiom and be done with it. Because all cases that we are interested in do have functorial factorizations. You really have to find a kind of a convoluted example not to have a functorial factorization. So it's easier to just assume that you have one, and yeah. You can still do most of the proofs I'm going to do after, but some of them it's like a shortcut. Okay. Are there any questions before I continue? No? Okay. Okay, so let's continue. So first, some terminology. A morphism in C cap W. So something which is at the same time a cofibration and a weak equivalence is called an acyclic cofibration. This is just a name. The intuition comes from topology or chain complexes, but just a name. Acyclic cofibration with something which is at the same time a cofibration and a weak equivalence. So something which I can draw like that. And similarly, as you can imagine, you have acyclic fibrations. Okay. Well, there is no special name for something which is at the same time a cofibration and a fibration. I mean, it's not something relevant. Maybe just one thing is that if you look at some books, they sometimes call them trivial cofibrations and trivial fibrations. This is just another name for this. Typically, it's not so used anymore because trivial fibrations in particular, one could think that it's a trivial fiber bundle, right? Which is not what it is. It's something different. Now, just to make sure, in topological spaces, fiber bundles, for example, of vector spaces are fibrations, and they're always acyclic because a vector space is contractible, so all the fibers are contractible, right? So it doesn't mean that the fiber bundle is trivial. It means that the two topological spaces are weakly homotopy equivalent. Okay. Okay. Bon, so this is just terminology. Okay. All right. Another terminology. Let I and P be two. Okay. We'll two morphisms. So I has the right lifting property with respect to P, which is the same thing as saying that P has the left. Sorry, I inverted both. So one thing to know, I'm a bit bad about right and left. So if you see an issue with that, just let me know. Because it's quite important, actually. Co-fibrations are on the left, vibrations are on the right. It's always like that. The right lifting property with respect to I, if. So this is the same thing. It's the same definition. Just in one case, I is the important part, or in the other case, P is the important part. But it's the same thing. If for every commutative square like that, sorry. And I didn't say it was a cofibration. There exists a lift. Okay. So it means that if you have if you have a commutative square where I is on the left and P is on the right, then there is a lift, whatever these two maps are. Okay. So for example, by MC4, maybe one notation. So what I'm going to denote as LLP, left lifting property, is the set of morphisms which have the left lifting property. Which, sorry, again, I inverted. So it's like that. It says that I has the left lifting property with respect to P, or P has the left lifting property with respect to I. Oh là là, décidément. Okay, so just a notation. This is a class of morphism. So it's going to be maybe a bit more clear once I state the obvious. So it's the axiom MC4 says that C is included in the set of morphism which have the left lifting property against all acyclic vibrations. And dually F is included in this thing, right? Axiom MC4 exactly says that every cofibration has the left lifting property with respect to all acyclic vibrations. And all vibrations have a right lifting property with respect to all acyclic cofibrations. Okay. Bon. Another notation which I may use from time to time is something like that, which I guess is a bit more visually pleasing. Well, the thing is to note that this is not a symmetric relation. Huh? Something can have a left listing property with respect to the other, but not the reverse. So it's not like orthogonality in geometry. Or another notation, again. So these are notations that you can find in some books, which is why I'm mentioning them. Instead of writing LLP of a class, you can write the class with a prescript perp. And similarly here. Like that. So these are all notations for the same thing. You fill in the blank. So we are going to make a lot of arguments about liftings and so on. So I want everyone to be on the same page about that. Huh? Okay. So far it's only terminology. Another piece of terminology, which is going to be quite relevant in what follows. So first a remark, C is complete. It admits a terminal object. And because it's co-complete, it has an initial object. So the terminal object, I will usually denote it like this, a star, which is meant to be like a singleton, a one-point set. And the initial object is the empty set in the category of sets. So this means, I don't know if everyone is familiar with this terminology. This means that for every A, there exists a unique morphism from A to the terminal objects. And here for all X, there exists a unique morphism from the initial object to X. Okay. Well, everyone is more or less okay with that. So example to think about in topological spaces, this would be a one-point topological space, and this would be the actual empty space. Just be careful. For example, in pointed topological spaces, this is also the one-point set, but this would be also the one-point set. In chain complexes, this would be the zero chain complex, and this would also be the zero chain complex. Okay. Okay, so examples to keep in mind. Okay, so definition now, an object X in M is called cofibrant if the unique morphism from the initial object to X is a cofibration. And it is said to be fibrant if the unique morphism from X to the terminal object is a fibration. Okay, so this notion is a bit more technical. It doesn't seem like much, but this is really going to be important in what follows. Just to give you an idea, cofibrant objects are going to be these, the objects which are good when you map out of them. Whereas fibrant objects are going to be those which are good when you map into them. So for example, Quillen complexes or injective complexes, and cofibrant objects you should think about as projective or CW complex. Okay, so this is quite important in the theory. Okay. So a remark, which is kind of a proposition, kind of a definition, kind of a remark. Every object admits two things: a functorial cofibrant replacement. So this is the definition part, functorial cofibrant replacement. The proposition is that every object admits one. And what it means is simply this. Okay, you apply Axiom Mc5, this one, to the unique map from the initial object to X. And so it admits a factorization like that. A cofibration followed by an acyclic fibration. And so this one here, sorry, blue is not good. This one is called cofibrant replacement. And as you can guess, usually, a functorial fibrant replacement. So X goes into Rx. So same deal. Huh? You apply Axiom Mc5 to the unique morphism from X to the terminal object. So this is fibrant replacement. So how to think about this property? This is kind of like the cellular approximation theorem. If we admit that cofibrant things are like CW complexes, this means that every object admits a CW complex, which is weakly equivalent to it. Okay, this guy is cofibrant and is weakly equivalent to X. Similarly, in simplicial sets, this is kind of like replacement as a can complex. It's something which is weakly equivalent to X and which is fibrant, i.e. can complex. Okay. Or in chain complexes, this would be a projective resolution or an injective resolution. Okay. So I hope you can kind of see now that this axiom Mc5 is quite strong, because a particular case is you apply this to this one, you take, for example, the zero chain complex. This means that every chain complex has an injective resolution, which, as you saw in the homology course, is not something obvious to prove. Huh? So this axiom is quite strong. Okay, everything good so far? Okay, okay. What to do? Maybe some examples of model categories. So the first one I'm going to state is quite obvious, but the next ones are very difficult, and proving that they are actually model structures is like chapter 2 and chapter 3 of this course. So just proving that there exists a model structure. So M, any category, complete and co-complete. Okay. So you have several choices. So these are not interesting examples of model categories. I want to be clear. This is a kind of a trivial example. So for weak equivalences, you can take all isomorphisms. For cofibration, you take everyone. And for fibrations, you take everyone. Okay, fair enough. Or you can do this. Or you can do this. Okay, and it's a small exercise to check that this is a model structure. As I said, it's not an interesting model structure, but it's one regardless. Maybe let's try to do the first one together. Just to show you what you have to check. You have to check 2 out of 3 for isomorphisms. So this is what we kind of did here. You have to check, well, that isomorphisms are preserved under retracts. So if you are, try to do it. It's a good exercise, really. Otherwise, the proof is in my notes. And for C and F, this is trivial because they are all morphisms. This one is also something that you have to check. You have to check that if you have a commutative square and this one or this one is an isomorphism, then there exists a lift. Okay, try to do it. You will see how it works. It's not very complicated, but it's instructive, I guess, is the word in English. And finally, there exist functorial factorizations. Well, you can just take this one to be x, and here you can C, and here you can take A. Okay, and so this is a factorization as an arbitrary map followed by an isomorphism, or an isomorphism followed by an arbitrary map. Okay. So really try to do it for the small exercise I left to do them, and also try to do it for the other 2 model structures. It's really interesting to see how it works. Okay. Bon, another thing, if M and M prime are model categories, then you can take their product. Okay. Also, if you have a model category, then you have its friend for free, which is the opposite category. So you take the same weak equivalences, but you reverse fibrations and cofibrations. Like that. So this looks a bit, I don't know, stupid, like what's the point? But actually it tells you that okay, the theory of model category is symmetric. And so if you have a statement about, let's say, fibrations, then you have a dual statement about cofibrations. And we are going to, well, most proofs, I am only going to do them for one of the 2, either cofibrations or fibration, and say it's dual for the other. There is going to be one part of the course where it's not going to be dual. It will be the small object argument. And for this one, if I'm being honest, there is, I guess, a co-small object argument that exists, but it's not useful at all because I'm getting ahead of myself. But in examples, we will often have small objects, but very rarely co-small objects. So this is something that's not dual because of examples. In examples, we will only have something on the source and not the target. Okay, so these are the trivial examples in a way. Now, more interesting ones. So the first example is due to Quillen, and is the category of topological spaces. So someone asked yesterday, yes, compactly generated weakly Hausdorff. So either you know what this is and you know why it has to be there, or you don't, and you don't have to care about that. Yeah, it's a technical condition on topological spaces that says that you have a good, an actual good category. So it has a model structure. So W are weak homotopy equivalences. C are Serre vibrations. F are Serre vibrations, of course. And C, so I haven't said it yet, but we can actually get away with only defining 2 out of the 3. But I can tell you right now what it is. These are retracts of generalized CW relative CW complexes. Okay, so what is this? If you don't know, so you start with a set A, then start with a set A, which you call A0. And then you glue a bunch of disks to it. Okay, so if you know CW complex, this is something that you should be a bit familiar with. So one thing to note, why is it called generalized CW complex? Because here you see I'm not starting with dimension 0. I'm not starting with vertices. You can start with any dimension. You can mix the dimensions together. It's not a problem. So that's the generalized part. Okay, then you do it again. You glue another bunch of disks to A1. Of course, and then you continue. A1, A2, start at A0. And you can do it an infinite number of times. And in fact, if you know what that means, you can even do it an uncountable number of times. Like, you can add a lot of cells. If you are not comfortable with that, you can just think about the countable case. So you had an infinite number of cells, an infinite number of times. And so you have a colimit. And this composite is called the relative CW complex. So you start with a space, that's the idea, you start with a space, you glue cells, and you glue cells again and again and again and again until you are tired, I guess, and then you have a relative CW complex, generalized. So the cofibrations are retracts of such maps. Okay, so it's a bit of a mouthful, but that's what it is. Okay, so that's the model structure of Quillen. And proving that it is an actual model structure is quite difficult. We are not even going to do it in this course, to be honest. It's hard. We are going to do it for chain complexes at first, and the idea is kind of similar, but this is a difficult problem. As a remark, all objects are fibrant, and cofibrant objects are generalized CW complexes. Because what is a cofibrant object? The map from the empty set, oh, so I should say retracts. The map from the empty set has to your space X has to be a retract of a relative thing. And so you start from the empty set, then you glue cells, and you glue cells, and you glue cells. So it's not a relative CW complex, it is a CW complex, an actual CW complex, or a retract thereof. Okay. Okay. So another example. As you can see here, I said a model structure. I didn't say the model structure. Why? Well, you already saw it on this example. You can have several different model structures on a category. And moreover, as I said, the weak equivalences are what's important. And here you can have two different model structures with the same weak equivalences. Okay, so the same spaces up to homotopy. But of course, not all of them are interesting. So here is another interesting one on topological spaces. So this one is due to Strum in 72. So you may not see it right now, but this one is not very natural because weak equivalences, I put quote, are strong homotopy equivalences. And this is not really natural. Model categories are designed for weak equivalences. But it turns out that it's possible also to put strong homotopy equivalences in this framework. So fibrations are Jurevich fibrations. So just to compare, before it was Serre fibrations, now it's Jurevich fibrations. So there are more fibrations, and there are less or fewer weak equivalences. And the cofibrations, you take, okay, again, a bit of a mouthful, retracts of Jurevich cofibrations with closed image. Okay. Not all Jurevich cofibrations have a closed image, so you take those which have, and you set retracts of such maps. Okay. And so for this one, all objects are fibrant and cofibrant. So this kind of makes sense because we haven't seen it yet, but why do we care about fibrant and cofibrant objects? As you saw in this thing here, these are the ones for which the Whitehead theorem is satisfied. So these for which weak homotopy equivalences are actual strong homotopy equivalences. So for the Quillen model structure, the cofibrant objects are the CW complex. So this makes sense. Huh? The Whitehead theorem is true for CW complexes. It's also true for generalized CW complexes, actually. Here, weak equivalences are already strong. So it makes sense that the Whitehead theorem works for everyone. Every weak equivalence is a strong equivalence because that's how we define them. Okay. And again, it's quite difficult to actually prove that this is a model structure. Because imagine you take a random continuous map, you have to factorize it as a cofibration followed by an acyclic fibration. And so you can try to say, okay, I will take the path space construction or the cylinder construction. But in some cases, it won't work. If your space is really awful space, this construction will not work. So it's quite tricky. Okay, so then prove that top has a mixed model structure where W is the W of Quillen and the F is the F of Strong. Okay. So if you recall, it has more weak equivalences than the thing of Strong. And it has fewer fibrations than the model structure of Quillen. And C is complicated. I don't want to go into it. Well, actually, you can describe it, but I don't want to spend too much time. Okay. Okay, so these are all examples of homotopy theories which fit into the framework of a model structure. So are there any questions so far? Feel free to interrupt at any point. Huh? I'm here to answer questions. If I don't answer questions, then you can just read my notes. I don't have much added value otherwise. No questions? Okay. Bon, another example. So this one is also. Yeah, une question? Ouais.
Are isomorphisms always weak equivalences?
So yes, this is going to follow from the axioms, but we are going to prove it today, actually. Yeah. But this follows from the axioms. So yeah, what I gave there is like kind of a minimal set of axioms. Then we are going to see a lot of properties which you can use freely. Okay, so another example of model structures is also due to Quillen. It's for the category of simplicial sets. So W are weak homotopy equivalences. C are inclusions. And F are can fibrations. Okay, so this is another example of model structures. And one which we are actually going to prove is a model structure in chapter 3, I guess. I don't remember the numbering. So in this one, all objects are cofibrants. And fibrant objects are can complexes by definition. Okay, so these are the objects for which the Whitehead theorem holds true, right? Okay. Alors, another example. If you take CH like that, okay, so to avoid the same question, let me put it Z here. I guess you can take any principal ideal domain, but So there is the projective model structure, where W are quasi-iso. C, this one is easier, C are surjections. And cofibrations are a bit complicated, so there are chain maps like that, such that the cokernel of I is projective. Okay, so projective, a module, a chain complex of projective Z modules. And IN is injective for N at least one. That's right. Did I write it wrong? Okay, one moment. I'm just checking if I'm writing the right thing. No, sorry. Sorry. The degree, at least one part is here. So again, fibrations are things which are surjective in positive degree. In degree 0, they may not be surjective. And also the cokernel in every degree is projective, a projective R module or Z module. Okay, another example, and the last one. So now we take non-positively graded chain complexes. For cofibration, you take injections in degree at least one, and F and here you take surjection with injective kernel. And sorry, I erased too much here. I is injective, but in all degrees. I just meant to erase at least one part. Okay, so maybe I will say it again so that everyone is clear. So this one is correct. Cofibrations are injection with projective cokernel, surjection in degree at least one. And here it's kind of reversed. You have injection in degree at least one and surjection with injective kernel. Okay. Bon. In particular, if you are working over a field, here I took Z, but you can take like a field. So you have vector spaces. Everyone is injective and projective. So you get injections and surjection in positive degree, or injections in positive degree and surjections. So exercise, try to understand why it's degree at least one here. Do it for the case of fields where it's a bit easier. So a hint has to do with this lifting property. Try to check that if you have a quasi-isomorphism which is injective here, then this map doesn't need to be surjective in degree 0 for the lift to exist. Ok, bon. Oui, tout à fait. Tout à fait. Je pense en termes cohomologiques, c'est pas bien. Voilà. Yeah, sorry, I was this is in positive cohomological degree, but so negative homological degree. Yeah. Okay, maybe I explain my comment right now. You have an isomorphism of categories between chain complexes graded in non-positive degree and cochain complexes graded in non-positive degree. Take Cn D. Okay, and here the differential lowers degree, so here it raises degree. Okay, so this is a bit artificial here. It's better to think about this as like cochain complexes, but this is just to show the kind of symmetry between the two. Okay, and this is an actual isomorphism of categories, no? Not even an equivalence, an isomorphism, which is not often that you have an isomorphism. Okay. So any questions so far? Okay, so once again, I would like to emphasize that it's not easy to prove that these are model structures. This one is what we are going to do in chapter 2, and it's going to take at least 3, even maybe 4 lectures. Okay, just to prove it's a model structure. And this one is going to be chapter 3, and it's going to take quite some time also. And it's not easy. One of the main things that I'm going to talk about in chapter 3 is the fact that this is it has this model structure, simplicial sets, and topological spaces have this other model structure. And what you saw in the homotopy theory 1 course is that it's the same thing. Doing homotopy theory in one is the same thing as doing homotopy in the other. So what I'm going to do in this first chapter, which is like a general chapter about model categories, is to introduce a notion of equivalences of model categories. And we are going to see that this model category is equivalent to this one. So this gives a foundational result that says that homotopy theory in this category is the same as homotopy category in the other. So if you don't like topological spaces because you have to care about properties such as completely generated with Hausdorff, so like me, you can do everything in simplicial sets. And if sometimes you need to go back to topological spaces, for example, you are working with manifolds or I don't know, or for example, fiber bundles, it's easier to define fiber bundles of topological spaces than simplicial sets. You can go back to topological spaces, and you know that is the same thing as staying in simplicial sets. Okay, so that's one of the main things we are going to see in this course. But there is a foundational basis to say that topological spaces and simplicial sets are the same up to homotopy. Okay. Are there any questions so far? No? Bon, so what we are going to do now is prove a few properties about model categories. So basic stuff that I'm going to use all the time. Okay. So the first one, or maybe first properties. So as you are going to see, model category Okay. I see there is a question. What do you mean that these models have the same homotopy theory? So this is actually one of the things we are going to do in this course, to define precisely what it means to have the same homotopy theory. Okay. So yeah. So I cannot tell you yet. One thing I can tell you actually is that if you look at all topological spaces up to weak equivalence, so it's not a set, right? It's a class because there is no set of all topological spaces. And you look at the same thing, but for simplicial sets, then there is something which is like a bijection, but these are not sets, so I cannot speak of a bijection, but it's like a bijection, which is in some sense factorial. Okay. So this is vague, I know, but we are going to have a precise definition later. Okay. So in all that follows, M, W, C, F is fixed. Okay. So M the category, W the weak occurrences, C the cofibration, and F the fibration. Okay. So let's go. So first of all, we saw that if I is a cofibration, this is one of the axioms, it has the left lifting property with respect to all acyclic fibrations. The content of this proposition is that it's an equivalence. If something has the left lifting property with respect to all acyclic fibrations, then it is a cofibration. Okay. Okay. There is more. Same thing for acyclic cofibrations and fibrations. The axiom MC4 states that you have this implication. What we are going to prove is the reverse implication. And it's not going to be obvious, just to be clear. Okay, there is a dual axiom, not axiom, proposition. Okay. Okay, so a morphism is a fibration if and only if it has the right lifting property with respect to acyclic cofibration. And similarly, but where you put the acyclic in front of fibration. Okay. So this one is, these two are dual to the first two axioms. If you apply this one to the opposite category, then you get these two. Oh, sorry. If you apply the 1 and 2 to the opposite category, you get 3 and 4 for free. So I'm only going to prove 1 and 2, and 3 and 4 will come from 3 just by duality. You write exactly the same proof, you just put all the arrows in the other direction. That's the proof. And finally, a morphism is in W if and only if it can be factored as P circle I, where P is an acyclic fibration and I is an acyclic cofibration. Okay. So this is not Axiom Mc5. In Axiom Mc5, only one of the two is acyclic. Here, both are acyclic. So it's a special case. Okay. So let me do the proof, and then I'm going to explain what are the consequences, because this is quite an important property. So let's prove one. So if I is in C, then I is in LLP of the value cap F by MC4. Okay, this was the axiom. So this one is trivial by definition of model category. The one we want is the reverse implication. So let us assume that I has a left listing property with respect to all acyclic vibration. So this first proof, it's not going to seem difficult when I write it. Every step is easy. The difficult part is, of course, to think about it. Of course, I'm not claiming I came up with it. Let's be clear, I did not invent model categories, but to think about how to go about it is the difficult part. And it's really a good exercise to try to do it again at home without looking at the proof. Because this is really a typical example of a proof in a model category. You play with commutative squares and lifting properties and so on, and things work out. It's quite, you'll see. Okay. So we have a map, a morphism I, which has the left lifting property with respect to acyclic vibration. How to prove that it's a cofibration? So let's go back to our axioms. When can we deduce that something is a cofibration? Well, if we look, there is only one, MC3. It's the only axiom in which we can deduce that something is a cofibration. So we want to apply MC3. So we want, and I did not write it again, but a retract, something like that. So if somehow we manage to fill this where this is a cofibration, then we are good. I is a cofibration. Okay. Bon. So okay, we know what axiom to apply, but we don't know to which morphism to apply it to. Bon. Now let's go back to our thing. We have a hypothesis which is about acyclic vibrations. What can we do? Well, there is not much we can do. There is one way to produce acyclic vibrations, and it's Axiom Mc5. So let's try. So by MC5, so let's see that it's like that. I can be factored like that. This is I, this is J, and this is P. Okay. So it would be great if we could find a commutative square where I is here and P is here. Because then we can apply our hypothesis. But I has the left listing property with respect to P. Bon. Can we find something like that? Well, yes, we can. This is a commutative square. Okay, so let me read better. This is a commutative square. This commutative triangle is the same thing as this commutative square. So there exists a lift here. L. So there is a morphism L from X to B, so that L circle I is J, and P circle L is the identity of X. Okay so far? Bon. So this starts to look like something that could be a restrict, right? If we put X on the bottom and B here and X here, and here we put L and here we put P, this is the identity. So this starts to look like a retract. B, sorry, X is a retract of B already. Now we need to do the same thing with the source. And of course, our goal is to have something like that. Okay. So who do we put here? Bon, I'm not letting you spend too much time. Simply put A again. Okay. Let me put some space. Okay. Well, here, this is the map J that was part of our factorization. So let's check. Is this diagram commutative? Okay, so if we start from the top A, we go to this part, and then we go to B, we have the morphism J. If we go here and we go here, we have L circle I, and L circle I is equal to J. So, okay. And now if we start from this A, we go here, then here we have I. And if we start here, then here, we have P circle J, and P circle J is I. So this commutes. So I is a retract of J. But J is a cofibration. Therefore, by MC3, I is a cofibration. Okay. So this is really a typical example of a proof in a model category. Okay. Are there any questions on the proof? No? Okay. Well, so as I said, point 3 and 4 are dual to point I, to point 1 and 2. So point 1 is dual to point 3, point 2 is dual to point 4. Point 2, you can prove it the same, pretty much the same way, so I'm not going to do it. It's not dual, but it's really similar. So I'm not writing it down. Let me do 5. So we have 2 implications to prove. So the easier one is this one. Assume F is P circle I, where P is in W, cap F, I is in W, cap C. Okay. Then we have a commutative triangle like that, F, P, I. This one is an acyclic vibration. This one is an acyclic cofibration. So by 2 out of 3, F is in W. You have a triangle, 2 sides are in W, therefore the third is in W. Okay, so this one is not difficult. Now the reverse, well, it's not much more difficult. So assume F is in W. By MC5, we can factor it, for example, like that, a cofibration followed by an acyclic fibration. Okay. But again, we have a triangle. Two sides are in W, therefore, by MC2, I is in W. And therefore, F is P circle I, where P is an acyclic fibration and I is an acyclic cofibration. Okay, so bon, this proof is not that difficult. Bon, this doesn't look like much, but actually it has quite a few consequences. So first corollary, and this is something that you are going to see quite often. If M, W, C, F is a model category, then it's kind of a 2 out of 3 thing. Out of the 3 classes WCF, if we know 2, we know then. So what do I mean by that? I mean that, okay, if you want to define a model category, you only need to give 2 classes out of the 3. Okay. You can either say, okay, I know cofibrations and weak occurrences, and therefore I will know fibrations. Or you can say, I know weak occurrences and fibration, and therefore I will know cofibration. Or this one is less common, but still it's possible. You know cofibrations and fibrations, and weak occurrences will be uniquely determined. There is a big if there, is this one. If you have a model category. So when I say you can only define a model category using 2 classes out of 3, you have to be careful. You can always say, okay, I want W to be this and C to be that. The F will be uniquely determined, but it doesn't mean that it will satisfy the axioms of a model category. For example, there is a necessary condition, W has to satisfy 2 out of 3, otherwise nothing works. Your 2 classes have to be closed under retracts, otherwise it doesn't work. So these ones typically are satisfied in examples. The hard part will be to prove the lifting property and the factorization property. Bon, the proof using the property we just saw. So if we know C and W, then F will be this thing here. The thing which have the right lifting property with respect to acyclic cofibrations. And you know what this is because you know at the same time C and F. So you know their intersection, and so you know the class of maps which have the right lifting property. So of course I say no in an abstract way. It means that it's uniquely determined by the data. Doesn't mean that it's easy to compute. That's also a big thing. Is very often you will define a model structure by two classes, prove that it's a model structure, and there will still be the question of what exactly is the third class. What is it composed of? Just like I stated here. In Cole's model structure, Cole's prove that it is a model structure. It doesn't tell you what, it tells you what C is. It's the set of maps which have the left lifting property with respect to each configuration. To actually know what these maps are, it's not easy. We don't want to classify maps as things which have a lefting property. It's complicated. The question is there an easier description? Okay, if we know F and W, then C, of course, is this part here. Bon, and this one is pretty, is not very useful in practice because, as I said at the beginning, W is the interesting part. So typically, you know what you want W to be. But if somehow you know C and F, then W, well, you can write it as this. And this, you can write it as this. So it's a bit convoluted. A weak equivalence is a map which factors has two maps. The first one has the left lifting property with respect to fibration, and the second one has the right lifting property with respect to cofibration. So as you can see, this is not a useful characterization in general, but it has the merit of existing. So I'm writing it now. Okay. And so just to emphasize, this is something that we do often. We say a model structure, for example, this one here, the strong model structure, typically we would only say these two. This one would be determined, and it's the most complicated, so it's the one we don't say. Or here, typically we would say these two. Or here for chain complexes, why was I not sure which one? Because the way I remember it is that it's quasi-isomorphisms and surjections in positive degree. And then cofibrations are necessarily something. Or similarly here. Okay. Questions so far? So this proof is really typical of proofs in model category theory. This is a really important corollary because very, very, very often you will see the model structure where weak equivalences are blah, 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 and fibrations are blah, blah, blah. And you will not see where the definition of cofibrations is. That's normal. It's determined by the data. Okay, another thing is the following. C, W, and F are closed under composition, which is not obvious. Well, for W, this is 2 out of 3. If you have a composable like that, 2 sides are weak equivalences, therefore the third is. Alors, there is a question. Are there some iterative method where we say enrich? Okay, so I don't think you can start with arbitrary data, but this kind of iterative method is going to appear, for example, in the small object argument to show that, well, the small object argument is going to be that you can factor any map for example, let's say this one, as an acyclic vibration followed by a cofibration, because this is really the hard part, the factorization. This is really the most difficult part of any proof that something is a model structure. Yeah, I mean, yeah, if you start from random data, yeah, probably. One thing that is maybe not clear in what I'm saying is that typically W, you don't choose it. It chooses you. The W is something that is natural, but you don't want to touch. Like in topological spaces, you don't want something else as W. You want weak homotopy equivalence because that's what that's the basic problem. And then fibrations and cofibration come after. These are the extra data, but this one you typically never want to touch it. Okay. Okay, so for C and F, so the proofs are dual. So I'm only going to do one. I'm not going to do the other. Let's say I'm going to do for cofibrations. So let I and J be two composable cofibrations. Okay, so we want to prove that J circle I is a cofibration. So we need J circle I to be a cofibration. And as we saw, a cofibration is something which has the lifting property with respect to acyclic fibrations. So we are going to prove that J circle I has the lifting property with respect to acyclic fibrations. So we do it like that. We start with a commutative diagram in which here this is an acyclic vibration and on the left it's our map, I and J. And we want to show that there exists a lift. So this is going to sound a bit like abstract nonsense. Or I don't know. But what you do, first of all, you rewrite your diagram like this. Okay. Same diagram. I just see it as a rectangle in this way rather than the other. Huh? It's the same diagram. So now, by MC4, there exists a lift L1. Okay. So I have a lift. And now I draw another diagram. Like that. Okay, I just take this triangle here and I notice it's actually a square with a flat edge, right? And so by MC4, there exists a lift L2. So we do have constructed a map from C to X. Now the question is, does it make this thing here commute? So I'm going to use some colors. Let me know if you don't see them well. So this triangle is this triangle. So it commutes because our lift commutes. now we have this. No, PGF. So another color. So we have this triangle is actually this whole square. I hope nobody is colorblind. So this triangle is this triangle. And finally, this triangle is this triangle. Bon, this looks like a lot of child's coloring, but maybe I can write a concrete proof. Let's see, this is F and G, F and G. So we have P circle L1 is G circle J, and L1 circle I is F. And here we have P circle L2 is G, and we have L2 circle J is L1. So now you combine these equations, and you see that P circle L2 is G. Well, this is a purple triangle. And now L2 circle J circle I is L1 circle I is F. Okay. Bon. You can choose the proof you want. Personally, I prefer to view it as commutative diagrams because otherwise it's a nightmare. But if you are not convinced, then this is the proof. Okay. Well, so if we recap, we have proved that if you have two cofibrations, then their composite is also a cofibration because it has the lifting property against all acyclic fibrations. Okay. And this is also a technique which is very typical in model categories. To prove that something is a cofibration or an acyclic fibration or whatever, you prove it using the lifting properties. This is really, really common. Any questions before I go on? No? Okay. Alors, another corollary, which is the question that was asked earlier. Isomorphism are weak equivalences, cofibrations, and fibrations at the same time, always. Proof? Well, to prove that it's, for example, a cofibration, we need to prove that it has the lifting property against all acyclic fibrations. So let F from A to B be an isomorphism, and G from B to A inverse. And let's assume that we have a diagram like this. And we want to prove that there exists a lift. Bon, any guesses? Let's say this is alpha, beta, and P. I want to define a map from B to X. I don't have much choice, just given this data. To go from B to X, well, I can use my inverse to go to A. And then I can use my map alpha. Fair enough. Now P circle L is P circle G circle alpha. No. quoi? P circle alpha circle G. Okay, but P circle alpha, because the square commute is beta circle F circle G. So this is beta. And now L circle F is alpha circle G, circle F circle G. And because G is inverse to F, this is alpha. Okay. So the two triangles commute. You see here, I haven't used in any way that this was an acyclic vibration. What I'm saying is that isomorphism have the right or left tilting property with respect to anything. You can always find a lift pretty explicitly. You just compose the correct mat with the inverse. Okay. Well, last property I want to show today. And well, I don't know. I know it's already late, so I don't want to go over time, even if we started a bit later. Just let me know when you want to stop. Well, no, we'll stop at the usual time, and then we try to make up next time. Well, so last property, and it's also quite important. So cofibrations and acyclic cofibrations are closed under push-outs. Fibrations and acyclic cofibrations are closed under pullbacks. Okay, what does this mean if you are not familiar with this terminology? Suppose so I'm going to state one of them and you can well, okay, I'm going to say both. So let's assume that you have a push out like that. So Y is B cup X over A. Okay, so it satisfies the universal property of push outs, which I hope everyone is familiar with. So there is a canonically induced map here. And J is a cofibration or an acyclic cofibration. Okay, that's what it means. And similarly for fibrations. For fibration, if, okay, I will write it because there is a potential for ambiguity. Suppose we have a pullback like this. X, Y, Z, X cross Z over Y. Then Q is a fibration or an acyclic fibration. Okay. So the way to think about it is if you push forward a cofibration, then you keep a cofibration, similarly for fibration, and similarly if it's acyclic. So be very careful about what I said last. Weak equivalences in general are not closed under push-outs or pullbacks. If you have a weak equivalence here and you push it forward, it may not be a weak equivalence. It's only if it's a cofibration, which is a weak equivalence, that you get the cofibration, which is a weak equivalence, and therefore a weak equivalence. That's a way of proving that if you push forward something, it's still a weak equivalence. It's only if it's a cofibration. There are trivial counterexamples in topological spaces. Bon, since I only have 2 minutes left, I'm not going to write them down, but bon, allez, soyons fous. Qu'est-ce qu'on pourrait faire? Bon, oui, allez. Okay, so no, this one is bad. Okay, I'm not going to be able to do it off the top of my head, but try to find a counterexample where you have a weak equivalence here, but you push it forward and it's not a weak equivalence. Well, I want to finish with this proof. So if you have somewhere to be, I know it's Friday night, so feel free to leave. It's in my notes. It's recorded. It's recorded from last year. So I just want to finish this proof. I won't be offended if you leave right now. I know it's time. So assume you are in this situation. Where I is in C, we want J in T. Okay, that's the goal. So typical approach, we prove that it has the lifting property against all acyclic vibrations. So we put a diagram like this. Okay, B is bad. C. Allez, tac. Voilà. Alpha, beta, J. Is there a lift? Bon, how do we define a lift? Well, this is a push forward. This is it's like an amalgamated sum. So it's B cup X over A. So to define the lift, we need to define a map from B and a map from X, which agree on A. How do we do that? Sorry, E. So we want to define a map into B. So F, G, J, I. Well, first of all, the map from B into E. No, the 0, 1 is this one. From X into E, you just take alpha. But you want to define the map from B into E. So how do you go about it? Well, you use your lifting property. Because now you have this diagram. So P here from A into E, it's alpha circle F. Here it's I. And here it's G. No, beta circle G. Okay, so now you are in your situation where you can use MC4. Not unique. Exist a lift by MC4. And so you have your lift L here. Maybe I'll do it in red. Up. And so you have an induced map here, which goes from Y into E. And I let you check that this is the L prime that you want, and that it makes the relevant triangles commute. Little exercise. Okay, so we are at the end of the session. So I'm going to stop the recording.